Hello students, welcome back. Previously we discussed groups and rings. Groups, well that was simple because we had only one operation to deal with. We need associativity, identity, and inverse. Because we have inverse, we can consider inverse operation. For example, if you have additive group, then we can consider subtraction. If you have multiplicative group, then you can consider division. That's all because of this inverse property. Now, if a group satisfies another condition here, the commutativity, then the group is called an abelian group. We went through examples like those, both abelian and non-abelian. Now, how about rings? Rings are tougher because we have to consider two operations. First, four properties are associated to a ring being an abelian group under addition. Okay. And then we have another property, but this one is about multiplication. Let me highlight it in different color. Let's see. I thought I did it. Somehow. Okay, I got it. All right. I highlighted in purple. I was gonna get brown, but somehow I wasn't getting it. Anyway, okay. I highlighted in purple. So associativity of multiplication. And that's the only property about multiplication and rings. Distributivity, on the other hand, is the property that's associated to both addition and multiplication put together. So that's a little bit different. As far as the multiplication is concerned, we have only one property here. So, in order to get a multiplicative group, we still have a long way to go. We have this, we need the identity, we need the inverse, and if you want a abelian group, then we need commutativity. So, including one more property, and one more property like these, we're going to get stronger and stronger rings. Including the commutativity condition, we get a commutative ring, excuse me. So commutativity of multiplication is included in, then we get commutative ring. And then the multiplicative identity condition is included in, and that's called the ring with unity, because multiplicative identity is called unity because we don't want to get confusion. The term identity is already taken by additive identity, so we usually use the term unity. And now, with all these, commutative ring with unity and further zero divisor property, and that kind of ring is called an integral domain. And examples of integral domains included not just things like integers that are simple, but set of polynomials with real coefficient, for example, like this. How do you solve a quadratic equation? We factor it, and we get blue times green is equal to 0, like this. So that we get blue is equal to 0, or green is equal to 0 using this no divisor property for integral domains, so that we get blue solution, green solution like this. And then if you have higher degree, you can factor and do the same thing. Everything follows from this property here, zero divisor property. So we are talking about something important. And these are the kind of things we will study in the second 1/3 of the course when we do ring theory. By the way, here are some examples. Set of integers with addition and multiplication. Set of polynomials with real coefficients under addition and multiplication. They're all commutative rings with unity with no zero divisor, so they're all integral domains. Some other examples. Well, here's an example of a non-commutative ring, matrix ring, n by n matrix, so we have multiplication, but addition, multiplication, all, yeah. And then we have, let's see, we have ring with this has unity. Let's see, we have identity matrix. So this one has non-commutative ring, but it has unity. So non-commutative ring with unity. How about ring with no unity? Can you think of an example that there's no 1 or something that will replace 1, like identity matrix? Well, here's an example. Take the set of all even integers. So even number plus even number is an even number, so it's closed under addition. Even number times even number is also even number, so it's closed under multiplication as well. And then we have all these properties, yes, yes, and yes. It has commutativity as well, but it has no unity. We need 1, but 1 is not an even number. We can create an example like that to matrices. Get a set of matrices, square matrices of even integer entries. And then it's easy to see that this is closed under matrix addition and matrix multiplication, because even number plus even number is even, and even number times even number is even as well. But there's no unity. The identity matrix requires 1s in the principal diagonal, but there's no 1 here. They're all even integers. Okay, so much for rings. Now let's go to field. The bulk of field theory will be covered in abstract algebra 2, but some part of it do appear in abstract algebra 1, partly in group theory and partly in ring theory as some special cases. So you gotta know what a field is. Basically, you have an abelian group for both addition and multiplication. So, association of addition and multiplication. Okay, so we use purple, right? For this when we did ring theory, yeah. And commutativity of addition and multiplication. So we have commutativity as well. So we have ring, we have commutative ring, and distributivity. We have this and that, but we don't need the second distributivity because left multiplication and right multiplication are the same in this case. Additive identity, of course, yeah, but multiplicative identity is added, so we have unity. So we are talking about ring of unity as well. So commutative ring with unity, and then furthermore, one more, additive inverse, yeah, that's for certain, but also multiplicative inverse as well. In short, we have additive abelian group and multiplicative abelian group put together. And when you get multiplicative group, we have to exclude 0, because it is possible to prove that 0 times anything is 0. As a matter of fact, we will prove it. We'll prove it in ring theory in this class. So, excluding 0, we get a multiplicative group, and that group is abelian too. So both addition and multiplication form abelian groups. So this is very, very powerful. In summary, we have this kind of Venn diagram. The big box is ring, and then we have commutative ring here, and rings with unity there. And then in the middle, we'll have commutative ring with unity. And then restricting further inside, we have integral domains. Fields goes even further, so that's something very powerful. Examples are like these. Rational numbers, real numbers, complex numbers, those kind of thing. We have not only addition and multiplication, but also they're both invertible. So subtraction and also division. Yeah, division is important. Division is also valid. Another example I can think of is a set of rational functions, polynomial over polynomial, where the denominator is not constantly equal to 0, those kind of things. Okay, so much for fields. And the others, let's stop here. Let's cover the others in a separate video, and that separate video will be an optional video.